Hi everyone. So in this video, we're going to get back to talking about solids of revolution. So these solids that we get by taking a two-dimensional region and revolving it around an axis. But we're going to see that there's a different method. So, in previous videos, we had talked about what we called the disk method and the washer method. So those are methods where you did this integral, and where the integral came from was this idea of adding up like a stack of disks or a stack of washers. So basically it was like you're taking your solid and you were slicing it right into these circular slices. And so in this video, we'll see that there's a different method, a different way of kind of taking your three-dimensional object and breaking it down into small pieces that in some situations will make finding the volume a lot easier, or there will be some cases where this will be the only method that will work. So I want to start by looking at an example as kind of a jumping off point for seeing why we need this new method. And then we'll talk about the general kind of formula and setup, and then we'll do 3 more examples. So yeah, let's get into it. So this question is asking us to find the volume of the solid generated by revolving the region bounded by y is equal to 2x squared minus x cubed, and y is equal to 0 about the y-axis. So by the way, this graph I have here, this is a portion. So the graph actually continues. It looks kind of like this. But I just took the portion of the graph that we actually need, which is this part right here, because we're going to bound that up with y is equal to 0, which gives us this. And so this is the region we're talking about. And we're going to revolve this region about the y-axis. So I'm going to start by just drawing the kind of two-dimensional picture of what this looks like. So something like that. Let me make that a little better. Maybe more like that. But then remember, this is a three-dimensional object. So this one, I'm gonna kind of draw in some three-dimensional stuff, and then I'll probably actually erase it out afterwards because I think it will kind of clutter up the picture. But basically, from the outside, this thing would look kind of like if you picture like a bowl that like a dog or cat would drink water out of. It kind of would look like that, like a bowl that's kind of curved up on the outside, and then on the inside it would kind of have this like rounded shape. So I actually just want to quickly show you a video that it's not this exact same solid, but it's a similar one that will just maybe give you an idea of what the shape would look like. So this is just going to show what it would look like to take a similar region and rotate it around the y-axis. Sorry, this video, the animation is very slow. But this is what we want to be kind of picturing for this shape, right? So it's from the outside, it's this kind of curved shape, but then the inside is also curved. Okay, so let's get back to this example. So why can we, why do we need a new approach for this? Well, let's say we tried to use we would have to use the washer method in this case, right? Not disks, because there would be a hole in the middle. So if we tried to use the washer method, we would have our inner radius and our outer radius, right? And so it would look something like this. And so theoretically, if you could figure out, what the inner and outer radius are, you could totally use the washer method on this. But the problem is, if you look at finding the inner and outer radius, so, maybe you start with the inner radius, notice that the inner radius is determined by this function, right? Y is equal to 2x squared minus x cubed. But then if you go and try to find the outer radius, well, that is actually determined by the same graph. And actually, we would need to be integrating with respect to y to even do this, right? Because when you're using the disk method, you would be stacking these disks vertically, and so we'd be integrating with respect to y. So first of all, we would need to solve this equation to get it in terms of being a function of y instead of x, and that is not an easy thing to do. And then additionally, I think the main thing that stands out to me here is that usually when we use the washer method, we have like 2 different functions for the inner and outer radius. And in this case, it's really the same graph. And so it's just not really clear how you would be able to do this with washers. And so what we're going to do instead is we're going to, rather than taking the solid and breaking it up by like slicing it into, you know, this stack of washers. Instead, we're going to take this solid and we're going to break it up into these cylinders that kind of nest one inside the other. So I'm going to draw in a sample cylinder, and then I'll show you an animation that I think will help you kind of understand it a little bit better. So something like this. So basically, I'm going to draw a few more to kind of show you the idea, but you can picture that this solid could be built up out of these nesting cylinders, one inside the other. So I just drew one there. You know, you could have another one here. And maybe I'll do a bigger one, so you could have a bigger one out here. And picture that they're like one inside the other, and that's what that word nesting means. And if you have infinitely many of these, you could construct this entire shape right out of these cylinders. So let me go back to this video that I think will show you maybe a little better than I can describe in words what's going on here. So basically, if we take this shape, and sorry, I forgot to speed this up because it's a very slow animation, so let me put it on 1.5. So if you take this region and break it up into slices, if you picture taking each one of these vertical slices and rotating it around, you get these cylinders, right? Kind of looks like a Mario tube, right? And so now it's going to show, you know, if you do that with a bunch of the slices, well, you get these nesting cylinders, right? And then if you look at what this whole solid looks like, it's not a perfect representation of the actual solid. So this will again remind you of what the actual solid looks like, right? So that's what the actual solid looks like. This is our like approximation of it. And so just the way that we can approximate things by slicing them, this is kind of just another way of taking this three-dimensional object and breaking it into pieces. I know that this is hard to picture. I think a lot of people have a hard time visualizing this. And I really appreciate if anyone finds, you know, I haven't been able to find the best resources for visualizing this. So if you find something that you think would be helpful to others, send me an email and I'll send it out to everyone, or you could post it on the discussion board, but send it to me as an email as well, because I would be really interested to see. But yeah, if you look around on YouTube, you can probably find, you know, some examples of animations for specific functions, but I haven't been able to find like a tool like the one that I showed you for the disk and washer method. Okay, so yeah, so this idea again is that we're taking this function and we're breaking it into these nesting cylinders. So one other analogy that people sometimes use to describe what these cylinders look like is, if you've ever seen these dolls, they're called Matryoshka dolls. They're like these Russian dolls where you have one bigger one and then a smaller one that fits inside of that, and a smaller one that fits inside of that, a smaller one that fits inside of that, and so on. So, you know, separately, they're all these kind of individual things, but when you put them together, they kind of become like one solid object. And so you can think of that as another analogy for what's going on here. We have these cylinders that each kind of fit one within the other, and once you put them all together, you get something that's kind of like a solid object. So we're going to use this idea to figure out a new way to use integrals to find the volume. So I want to go over here and just kind of write down the general approach here, and then we'll go back and do it with that specific example. So this is usually referred to as the shell method. So the cylinders that we saw in that animation, or that we drew in the previous one, those are usually referred to as cylindrical shells. And I'm not exactly sure why the word shell is used, but yeah, that's basically the general word that's used. Sometimes people use tubes, so they'll call it the tube method. But yeah, I'll be calling it the shell method in this class. And so basically the way that the shell method works, so I'm just going to draw some function here. So say we have a function that has been rotated around the y-axis in this case. So as we drew in the other picture, we can approximate this volume by breaking it down into these shells. And so each of these shells, I'm just going to kind of draw one out here. You know, in the picture, I drew it as just being kind of a flat object, but really they have some thickness to them, right? And I generally will not draw them with the thickness in the picture just because it gets a little too cluttered. But you want to imagine that they do have some thickness to them. Okay, so let's kind of write down some of the stuff we've been talking about here. So we said that a volume of revolution can be approximated, or let me say it this way, sorry, the volume of a solid of revolution can be approximated by adding up the volumes of these nesting cylindrical shells. So again, that word nesting just means you have one fitting within the other one within the other one. Okay, so let me kind of write that out as a mathematical statement. So the volume would be approximately equal to the sum from 1 to n of VI, where I'm saying VI to refer to the volume of the ith shell, right? So you would be adding up, you'd have like a really tiny one on the inside, and then you'd add up the next one, and so on. And you'd go through and add up all the volumes of these different cylinders. And if you add them all together, you'll get an approximation of the actual volume. So in order to figure out how to actually kind of do this, we need to figure out what is the volume of one of these cylindrical shells. So let's go back to this picture here and think about how you would find the volume of a shape like this. So basically, what we're going to do is going to be more of like an approximation of the volume, but the volume is going to be approximately equal to, so the volume of the ith shell is going to be approximately equal to, if you take 2 pi times the radius, and so I'm going to use r with a subscript of I. That's just to refer to, the radius is going to be different depending which cylinder you're looking at, right? If you're here, the radius is going to be smaller than it was in the blue one, right? So when I say VI and RI, that's just a way of denoting, maybe we're talking about the first cylinder, maybe we're talking about the second one, maybe we're talking about the third one, and each of those is going to have a different radius. So the volume of the first one will be talking about R1, the volume of the second one will be talking about R2, and so on. And then we also want to multiply that by HI. And then we're going to multiply by one more thing, but I want to talk about what this means. So what does it mean to multiply 2 pi times the radius times the height? Well, if you take the radius and multiply 2 pi times the radius, that would give you the circumference, right? 2 pi r is the circumference. And then if you take that and multiply by the height, that basically gives you the surface area of this cylinder. And let me draw this one other way that I think might be kind of helpful. So if you were to take the cylinder and unwind it and make it into like a rectangle, right? If you just kind of cut it and peeled it open. Well, then if you were to look at the distance along the top, the distance along the top would be 2 pi times Ri, right? Because that's the circumference. And then if you multiply that by Hi, that would give you the area of this rectangle. But it's not just a rectangle, right? It has some three-dimensionality to it. And so we want to draw this with some thickness. And so we can call this thickness delta x. Right? So the thickness of this thing is delta x. And so the volume is approximately going to be equal to 2 pi times the radius times the height. Let me just color code that. And then times delta x. And that's not a perfect volume, and so I should really say V is approximately equal to. And the reason it's not perfect is because if you were to actually cut this open, you wouldn't get a perfect box because the inner and outer radius are different, but it's a fine approximation. And because when we're using this method, we're going to be thinking of using many, many very thin cylinders, it becomes a better and better approximation the more cylinders we have. So it will work just fine as an approximation. So I'm just going to go in and put that into our sum here to just get a little bit more specific. So another way of writing this would be the sum from 1 to n of, so we said 2 pi times the ith radius times the ith height, and then times delta x, which is the thickness. Okay, so how would we find the exact volume? We basically want to use infinitely many shells, right? So we need to bring the number of shells towards infinity. And so that's going to be a limit. So the exact volume is going to be equal to the limit as n approaches infinity of the sum from 1 to n of 2 pi times the ith radius times the ith height times delta x. And so what happens when we take a limit of a sum? Well, it turns into an integral, right? So we get the integral from a to b, and we'll talk about where those bounds come from in a minute. And then I'm just going to write it now as 2 pi times r times h dx. But one thing that's really important is that the radius and the height, those are both going to be functions of x. So these are going to be functions of x, and we'll talk about where exactly, what those come out to be in a moment. And so the general formula you want to know, this is basically like the shell method formula, is that the volume is going to be equal to, so we can pull the 2 pi out, right? Because that's just a constant. So 2 pi times the integral from a to b of r times h dx. So this is our shell method formula. So just to kind of add something to this picture up here to help you think about the bounds. So where are A and B coming from? They're basically just coming from what is the smallest and biggest radius that is going to occur in this specific shape. So in this case, the smallest radius would be here, right? This would be a radius of 0, so like a non-existent cylinder. And then the largest radius would be out here. So your bounds are basically going to come from what's the smallest and largest radius that it makes sense to plug in. Okay, so let's go back to our example and we'll see how you actually find the radius and the height for a given solid. So I'm gonna erase a couple of these because I think it will just make the picture more confusing if we have too much going on. Okay, so let's focus on this blue one. So what we need to do is we need to set up this integral. We know that we're going to be doing 2 pi times the integral from a to b, and we know that we're going to have some kind of a radius and some kind of a height, and we need to figure out what those are. Okay, so let's look at our picture here and let's look at the cylinder we drew. So the radius would be this distance here, right? This is our radius. So what is the radius going to be? Well, notice that we can draw a cylinder at any x value we want, right? So the radius is actually just going to be x. So again, why is that? It's because I erased them, but we had like other cylinders, right? And you can make a cylinder at any x value. And actually you have to, right? In order to really approximate this volume, we want to picture like infinitely many, picture like thousands of cylinders. And that means that you're going to have a cylinder with a radius at every x value between 0 and 2. And so that's why we're setting the radius to just be equal to x. And we'll see that in general, that's what's going to happen. I don't want you to always assume that's the case because we'll see in the next video some examples where that's not the case. But very commonly, the radius will just be equal to x or to y, depending on which variable you're integrating with respect to. And again, that's an issue we'll get into in the next video. In this video, we're always going to be integrating with respect to x. Okay, what about the height? So here's our height. So the height is going to be determined by the function, right? So again, if you're ever trying to figure out what's the height, think about if you're at a specific x value, what would you need to do in order to figure the height? So for example, here it looks like maybe our x value is, I don't know, 0.7. So imagine that you're trying to figure out what is this orange distance when x is equal to 0.7. Well, you would plug it into this equation, right? That is exactly how you would figure out that orange distance, because that's just the height of the function. So that means our height is 2x squared minus x cubed. And then what are our bounds? Well, we want to look at what is the smallest and the largest radius that makes sense in this picture. And so the smallest radius is going to be 0, and the biggest radius is going to be 2, right? So our A value is going to be 0, and our B value is going to be 2. So now we're ready to put all of that together. So the volume is going to be 2 pi times the integral from 0 to 2 of x times 2x squared minus x cubed dx. And so now we can just multiply this out and integrate it. So we're going to get 2x cubed minus x to the 4th. And now we're going to find our antiderivative. So the antiderivative of 2x cubed would be 2 over 4 x to the 4th. And then we have minus 1/5 x to the 5th. And then we're evaluating this at 2 and at 0. And so we get so when we plug in 2, so 2 over 4 is the same as 1/2, right? So we have this 2 pi on the outside, and then we have 1/2 times, so 2 to the 4th power is 16. And then we have minus 1/5, and 2 to the 5th power is 32. And so altogether, this gives us 2 pi times, so 1/2 of 16 is 8, minus 32 over 5. So now we can make a common denominator. So our common denominator is going to be 5. So that's 40 over 5 minus 32 over 5. And so that leaves us with 2 pi times 8 over 5. And so our final answer is 16 pi over 5. Okay, so we're going to do a few more examples. And basically, like I said, in this video, most of the examples we're going to do are going to be, I think, fairly straightforward. So they're all going to be integrating with respect to x. And yeah, the general approach is going to be about the same. But I would still recommend, checking out all the examples, because each of them is designed to kind of bring up something a little different that I think will be helpful for you to see. One thing I just want to mention, and we'll talk more about this a little bit later this week when we talk about how you can decide whether to use the shell method or the disk or washer method. Notice that when we revolve around the y-axis, we're actually integrating with respect to x. Whereas when you use the disk or washer method, if we were revolving around the y-axis, we would have to integrate with respect to y. And it's basically because of the direction of the thickness, right? So if we look at this picture here, delta x, and maybe I'll even draw it on this picture like this. So, if the cylinder has some thickness to it, delta x is a horizontal measurement, right? The thickness goes horizontal. And so that's where the dx comes from. Whereas when you're adding up disks or washers, well, then the thickness would be measured vertically, right? If you were revolving around the y-axis, you would have, like, if you had a washer, it would look like this. And so in that case, you would have delta y. And so that's why you integrate with respect to y. So if you're trying to look, what's the trick to remember? Basically, when you're using the shell method, whichever axis you're revolving around, you switch the variable. So when you're revolving around the y-axis, you integrate with respect to x. When you're revolving around the x-axis, you integrate with respect to y. And like I said, in this video, they're all going to be with respect to x, but we'll see some examples in the next video that are with respect to y. Okay, so we're going to next do an example that I think we did this example already in a previous video with washers, but I want to show how we can also do this with shells. So in this problem, we have the region bounded by y is equal to x squared, y is equal to 0, and x is equal to 2. So that's like that, and we're revolving it around the y-axis, so that's going to give us this shape. So it's going to look like this from the side. And then if we were to kind of think about this in a three-dimensional way, well, from the outside, it would actually just look like a cylinder, right? It would be like a glass, you know, that you would drink some water out of. But on the inside, it's curved. It has, you know, the sides of the inside of the cup are not straight. So you can totally do this using the washer method, right? You would have your inner radius would be this, your outer radius would be this. So the outer radius in this case would just be a constant function of 2. The inner radius, you would have to solve this equation to get it to be in terms of y, because if you were using washers, you would have to integrate with respect to y. But I want to see how we can do this with shells. So I'm just going to draw a sample cylinder. So I think a lot of students have trouble visualizing what the sample cylinder looks like. So I really want to walk you through how you can draw it. Basically, pick whatever x value you want. Pick some random x value. So I'm just going to go here and draw a vertical line at that x value. Then go across and symmetrically at like the kind of the same part of the shape, draw another vertical line. And this is making me realize that I need to fix this a little because it doesn't look quite right. It's not going to be as symmetrical as it should be. So maybe that will be better. So that would give us like something over here, right? If we're being symmetric. And yeah, I still didn't draw it perfectly. It should be at the same height, but we can pretend. So you do this kind of symmetric thing, and those are telling you where the sides of the cylinder are. And then you just go through and connect them with the circle. And then at the bottom, you do the same thing to kind of suggest this round shape. Okay, so what is our radius going to be in this case? Well, the radius, again, is just going to be x. And that's because we can make a cylinder with any radius, starting at 0 being the smallest, up to 2. And so r can be any x value. We want the radius just to be x. And then what about the height? Well, once again, the height is actually determined by the function, right? By this function, because if you go, you know, say that we're at like 1.2 or 1.3, if you wanted to figure out what the height was, you would just plug it into the function y is equal to x squared, and that would give you this orange distance. So the height is going to be equal to x squared. And so what would our integral look like? Well, now for, you know, adding up infinitely many of these, that turns into an integral. And so we're going to be integrating from, you know, some a to b of x, or sorry, let me first write it generally. So r times h dx. And so that is going to be 2 pi times the integral. So let's figure out what a and b are. Well, a is going to be 0. We already mentioned that because that is the smallest radius that makes sense in this picture. And then what's the biggest radius? It's 2. So our integral is going to go from 0 to 2. So we have the integral from 0 to 2 of x times x squared, and integrating with respect to x. So this one is going to be 2 pi times the integral from 0 to 2 of x cubed dx. And so what's this going to look like? Well, we'll have 2 pi times, so our antiderivative is going to be 1/4 x cubed, or sorry, 1/4 x to the 4th. And we're evaluating that at 2 and at 0. And so that gives us 2 pi times, so if we plug in 2 for x, we get 2 to the 4th, which is 16. So we have 1/4 times 16. And then 0, we'd get nothing, so we don't need to worry about that one. So that gives us 2 pi times 4, and that gives us 8 pi. And I would recommend, again, I'm not 100% sure if we did this example. I think we did, or maybe you did it on a worksheet, but try to do this by the washer method too, and you should see that even though your integral will look different, you'll get the same answer. Okay, so we're next going to look at an example that has one slight kind of twist to it, but otherwise very similar kind of setup to these other ones. So in this one, we're looking at the volume of the solid obtained by revolving the region bounded by y is equal to negative x squared plus 4x minus 3. So that's this is a parabola. You know, it would actually kind of go like this, but I only graphed the part of it that we actually need here because we're also including y is equal to 0. So that's giving us just this little kind of just the top of the parabola. And so that's the region. We're revolving this around the y-axis. So we're going to end up with something that looks like this. And this one, I think this will actually just look kind of confusing if I try to draw this three-dimensionally. So let me just try to describe it. So if you have like a bagel, so, you know, something that looks like this, but it's three-dimensional. Let me try to, I don't know if that's helping. I was trying to make it look three-dimensional, but I don't think that really helped. So let's say you have like a bagel or a donut, and then you cut it in half, like on the side, right? The same way if you have a bagel and you're like cutting it so that you can put some cream cheese on it, that's what this shape would look like. It would look like just the top half of a bagel, right? Because if you were to take a full, like something like this and revolve it around, that would give you basically a donut shape, but we only have the top half of it. So that's how you can visualize what this looks like. I just think if I tried to draw it in three-dimensionally, I think it would just make the picture look more confusing. Okay, so let's draw in one of the cylinders. So just going to pick a random x value. So let's maybe go here. I'm going to draw a vertical line. Then I'm going to go over to the same x value, but symmetrically across. And so those are the two sides of my cylinder. And then I'm just going to connect them with a circle like this. And then same thing at the bottom. So that is one of our cylindrical shells. Okay, so one thing you might notice that is a little different in this one is that it doesn't go all the way into 0, right? So this example started at 0. This picture I drew started at 0. This one started at 0. This one has like a hole in the middle. And so you might be wondering, does that affect what we use for R? And so we actually are still going to use the radius being equal to x. And so why is that? Well, the radius still is supposed to be like every single x value. But the only difference is that now the x values should start at 1, right? We don't want to include, like you wouldn't want to have a cylinder in here, right? That wouldn't make sense because that's not part of the shape. But the way that we accomplish that is by restricting the bounds. So if we make our first bound 1, and then our upper bound 3, and then we let R just be equal to x, that means that we'll be including all of the x values between 1 and 3. And that's what we want, right? We want to include 1.1, 1.2, 1.3, 1.4, like every single x value between 1 and 3. And so that's why we still set the radius equal to x. We don't say like 1 plus x or anything like that, because truly the radius just is equal to whatever x value you're at. It's just that the bounds need to be in place to restrict what that can be. And then how do you find the height? Well, the height is just equal to the function in this case, right? So the function is negative x squared plus 4x minus 3. So the height is equal to negative x squared plus 4x minus 3. And so now when we go and integrate this, we're going to have 2 pi times the integral from a to b of the radius times the height dx. And so that's going to be equal to 2 pi times the integral from 1 to 3, as we discussed, of x times negative x squared plus 4x minus 3 dx. So one thing I just want to quickly mention is that you may have noticed on all the examples we've done, and this actually will be the case for all the examples in this video, the radius is just x and the height is just the function. However, I don't want you to like memorize that as a rule and think, oh, it's just always going to be the integral of x times f of x, because that's not the case. We'll see in the next video that there are going to be some where the height is not just the function And there's going to be some where the radius is not just x. So it's really important that you draw a picture and look at your specific situation and just ask yourself, what is the radius, what is the height in this specific situation, rather than try to memorize a formula that is only going to work in certain situations. Okay, so we're going to now have the integral from 1 to 3 of negative x cubed plus 4x squared minus 3x. So this one's going to take a little bit longer to evaluate because we're plugging in 1 and 3. Rather, we're not plugging in 0 at all. So just kind of heads up on that. This might be a good one for you to kind of go off to the side and figure it out yourself first, rather than watching me do a lot of fraction arithmetic. Okay, so we'll have negative x to the 4th over 4 plus 4 over 3 times x cubed minus 3 over 2 x squared. And we're evaluating this at 3 and at 1. And I forgot a parenthesis. There we go. Okay, so this is going to be 2 pi times, so let's start by plugging in 3. So 3 is going to give us negative, so 3 to the 4th is 81. And then we get plus 4/3 times 3 to the 3rd is 27. And then we get minus 3/2 times 3 squared, which is 9. And then from that, we're going to subtract, plugging in 1, which just gives us negative 1/4 plus 4/3 minus 3/2. And let's actually combine these fractions, what we can, that already has the same denominator first, because we'll see that some stuff will simplify rather than try to make a common denominator right off the bat. So we're going to have negative 81 over 4 plus, so 4 times 27 is going to be 104. And then we have minus 27 over 2. And then to this, we're adding 1/4. And we're subtracting 4/3, and we are adding 3/2. Okay, so what is going to simplify here? Well, we can do negative 81 over 4 plus 1 over 4, so that's going to give us negative 80 over 4. So that's nice because that's going to be an integer. And then we have 100 over 3. And then we have, for the halves, we have negative 27 plus 3, so that's negative 24 over 2. And so that's going to be 12. So we now have 2 pi times negative 20 minus 12 plus 100 over 3. So this is going to be 2 pi times negative 32 plus 100 over 3. And so that's going to be equal to, if we make a common denominator of 3, negative 96 over 3 plus 100 over 3. And so that gives us 2 pi times 4 over 3. And so our final answer is going to be 8 pi over 3. All right, just one more example. So this example, I think the setup of it will be fairly simple, but we'll see that when we get to the actual integration step, there's something new that I just want to kind of point out. So in this case, we're working with y is equal to 1 over 1 plus x squared. So that, by the way, if you were to look at the full graph, it would look like this, but I just included the part that we actually want here because we're also bounding that with x is equal to 0, y is equal to 0, and x is equal to 2. So we're looking at this shape here. And we're taking this and we're revolving this around the y-axis. Let me do that a little better. I don't know if that's much better. And so we get a shape that looks like this. And maybe I'll just kind of add this three-dimensionality to it. So this is one that, one thing that might strike you as being a little different about this one is that it doesn't have any kind of like a hole in the middle. Like all of the other ones we did had some kind of, this one had a hole in the middle, this one had a hole in the middle, this one had a hole in the middle, this one doesn't. But you can still use shells on this. And so why would you use shells on this instead of like discs? Discs might seem simpler. Well, the problem is, again, if you wanted to use discs, you would have to be integrating with respect to y, right? Because the thickness is delta y. So if you're integrating with respect to y, that means that you need to solve this for x, and this is not the friendliest thing to solve for x. So, it's generally going to be easier in some cases, if using the disk method, even if that like seems like an easier setup to you, it might, the equations you have might make it more difficult to actually use the disk method. Okay, so let's see how this plays out. So I'm going to draw a sample cylinder. So how do we do that? We just go to a whatever x value, and then we go symmetrically across from it, and we connect it with a circle, and it goes like this. So this one doesn't have a hole in the middle. So what that just means is that, you would have like all the way kind of filling in, like you would even have, a cylinder in the middle like this, right? So, there's nothing wrong with it not having a hole in the middle. We can still fill it in with these nesting cylinders. Okay, so what is the radius going to be in this case? Well, no surprise here, it's going to be still just equal to x because, we can have any radius. We just saw that you can have one all the way in at 0 or close to 0, and then we'll go all the way out to 2. And then the height, again, no big surprise here, the height is just going to be the function. So the height is going to equal 1 over 1 plus x squared. And what are the bounds going to be? Well, a is the smallest value, and that is 0, and then b is the biggest value, and that is going to be 2. Okay, so what's our volume? So again, we have 2 pi times the integral from a to b of the radius times the height. And so in this case, that's going to be 2 pi times the integral from 0 to 2. It seems to be popular bounds in this video, of x times 1 over 1 plus x squared. Or what would be another way of writing that? Well, if we multiply these two things together, we're going to get x over 1 plus x squared. Okay. So if you were going to go integrate this, your first thought might be something with inverse tangent, right? Because we know that the derivative of inverse tangent is 1 over 1 plus x squared. However, we have an x in there, right? So that's not going to work. Like it's only if you have, 1 over 1 plus x squared or like 5 over 1 plus x squared that you can use inverse tangent. In this case, it's a completely different function. But what you might notice is that the derivative of the denominator is 2x, right? And then we have an x in the numerator. So that suggests to us that we could use a substitution. So we're going to do a substitution. We're going to set u equal to 1 plus x squared. And then du is going to be equal to 2x dx. So that means that du over 2x is going to be equal to dx. And then our new bounds are going to be u is equal to 1 plus 0 will be the lower bound. So that will just give us 1. And then the new upper bound is going to be 1 plus 2 squared, which is 5. Okay, so what is our new integral going to look like? Now we're going to have 2 pi times the integral from 1 to 5 of x over u du over 2x. And so we're going to cancel out this x and this x here. And so we can then pull that 1/2 outside of the integral, and that will just leave us with pi outside of the integral, right? Because 2 pi over 2. And so now we just have the integral from 1 to 5 of 1 over u du. Okay, so what is the antiderivative of 1 over u? Well, that's just ln of absolute value of u. So we have pi times ln of absolute value of u evaluated at 5 and at 1. So what do we get when we plug these things in? Well, we have pi times ln of 5. We don't need to put the absolute value, right, because 5 is already positive, minus ln of 1. And so ln of 1 is just equal to 0, right? Because ln of 1 is asking you, what power do I need to raise e to get 1? And the answer is 0. And so we're just left with pi times ln of 5. And that's our answer. All right, so that's it for this video. Like I said, in the next video, we'll do some more slightly different examples using this same shell method. And then the next video after that, we'll kind of do a total just review of volumes. So we'll talk about how you can decide whether to use the washer method, the shell method, or the disk method, and do some problems, just some more problems to practice with volumes. See you next time.